We ready? Good morning, everybody. I'm Jonathan. Hello. Hello. I also enjoyed the conference last night, but here I am by the power of coffee. I do PerlCon stuff. Most relevant to this talk, I've been pretty involved in the concurrency design of PerlCon. Not so much the syntax, much more the semantics, but I'm to blame for a little bit of the syntax too. I founded MoreVM, which is the runtime that we typically, or most people are running PerlCon on. I still play the architect role there. If you came to my talk on Wednesday, then I talked a lot about the optimization works that I do there. And I work on the Rīga compiler now and then as well. There was some time when I was the top committer there, and happily since then other people have taken up that mantle. So that's very nice. I always like it when people take work off me. And when I'm, or along with doing that, I work at a company called Edgement, and they're originally based in Sweden, but I lead the Prague office of Edgement, where I mostly work on developer tooling and consulting and compiler-related things. And at Edgement, we're building a couple of PerlCon things as well. Crow is a set of tools and libraries for building distributed systems. We'll talk about it a little bit more today. And also Comma, which is integrated development environment for PerlCon. And if that sounds exciting, then there's shiny leaflets on the table outside. So, today, I want to talk to you about three things. First, I want to talk to you about the essence of PerlCon concurrency. I want to try and distill it down to the underlying principles, some of the key mechanisms that are at work. And then once you have an idea of what all of this is, I want to talk about the application of PerlCon concurrency. And I'm very grateful to one of my customers who have allowed me to today talk a bit about an application that we've been building for them in PerlCon. And that application has made some quite good use of the parallelism and concurrency support in PerlCon. So it's going to be interesting to share a case story from a case study from a real application that I've been developing using this, and that's very exciting to be able to share. And then we'll finish up with just a few short words on where I think we're going next, because we don't stand still. We try to keep moving and making things better and better. Okay, so what's the essence of PerlCon concurrency? You know, for me, really, it's the essence of being a Perlish language itself. Whatever we end up resulting in with the naming discussion, there'll still always be a sense that PerlCon or Camellia, whatever, maybe we should just call it whatever, is, I'm joking. Call it star, yeah. But whatever happens there, we have some shared legacy of some key ideas, and that I think have played a very important role in all the Perls and all the languages of this family. So a Perlish language is proudly multi-paradigm. This is really important when we come to concurrency and parallelism, because we need different tools when we do different things. As the saying goes, if the only tool you have is a screwdriver, everything is pretty screwed. Concurrency is interesting. Actually, the etymology of concurrency is brilliant. Because in some languages, concurrency has come to mean doing multiple things at the same time, and in other languages, it went and took sort of a little diversion, and it means like competition between things, and the etymology has both. And what's really nice is that perfectly captures what's going on. Concurrency is about multiple different things going on, and they're normally competing over the same resources, and we need to try and bring some order out of that chaos. Concurrency is interesting because we don't really get to choose it. It chooses us. We don't say, oh, my web application is not going to be concurrent. People will nicely queue up and make a request to it one at a time. They won't. Or we're building the airport check-in system, and no, two people won't both go for the seat with the lots of legroom at the same time. That'll never happen. Oh yes, it will. This is something that's on us to deal with. So we need tools that help us model the concurrent problem domain. This is a modeling level problem, and then we sort of try to implement a solution that encompasses our model of how we cope with those things. Then we have parallelism. Parallelism is very, very different, because we choose it. We say, this thing takes too long. So what if we try to use multi-core hardware, CPUs with many cores that can do many things at once, in order to reduce the amount of time that we spend? So concurrency is part of the problem domain, and parallelism is part of the solution domain. So with parallelism, we kind of already have a solution. We just want to twiddle it enough to get it to run in parallel. They also have some quite different properties on correctness. Correctness with concurrency is horrible. It's domain specific. I can build something that looks very similar for two different systems in two different problem domains, and in one of them it can be a completely acceptable solution, and in another it can be a wildly wrong solution. Simply because it's the requirements on the system that determine whether it's correct. With parallelism, it's much easier. We already have an idea of what the answer is, and what we need is something that produces an equivalent result. That doesn't mean it has to be identical. So maybe in some problems, if we're searching for something and there's two solutions, which one of the two we find first doesn't really matter. Or perhaps if we're producing results, the order maybe doesn't matter for them to be equivalent. It depends. But overall, we can say that correctness is quite easy with parallelism because it's just equivalent results to the serial thing. So we need different tools for these. And even within them, there's more than one way to do it. There's different kinds of parallelism. So for example, if I look at my code, and my code is structurally doing one thing and then another thing, and the things are independent, we'll just do them at the same time. Maybe we'll cut the time close to half. On other situations, I might have something that looks like a loop, or a map, or a grep. And I say, okay, let's this time break the data up. And we break it up into batches, and we distribute the batches over the different cores. So this time, structurally, our program looks like a loop, and we just want to parallelize the loop. You can see that those are kind of different, and we want a different tool to do them. A tool that's good at the first could probably be pretty clumsy for the second. And concurrency is the same story. As I said, it's a modeling thing. How do I want to model my system? How can I look at the problem that I'm solving and map it into something that is nice to solve? Maybe object orientation will be useful. Maybe I'd like some concurrent objects where I do method calls on them, and the object has some kind of automatic protection that means only one of these calls happens at a time. So, each call takes the object from one good state into another good state. That's one way of looking at it, but sometimes, actually, it's much nicer to look at concurrent problems as event processing. Events are great because you can't argue with them. An event says, this thing happened, and all you get to do is react. And you just say, okay, this happened, this happened, this happened. We write an event processor that takes them and maybe has some current state of the world, maybe spits out its own events for downstream event processors to do. They're very different ways of looking at things, and they're both extremely useful. But again, they're different. And PerlCon provides for all of these and some more besides. Next, and I think this is really important, a Perlish language makes the easy things easy. Let's look at some code and see if that's the case with Perl 6 and concurrency. So here we start of an application, and we want to load some input, and we want to load some configuration file. And excuse the structuring, so it's easy to turn it into the parallel version, but I'm just doing a list assignment here, and then I'm saying load this YAML by slurping this file and pass the YAML. Here we just do some JSON. So how hard is it to turn this into a parallel program and do these two at once? It's that. We just say start and start this, and that starts them off. It throws them off onto a thread pool, gets them going in parallel, and they both produce an object called a promise. And the promise is a way of saying, well, we promise to have a result in the future, either success or maybe an exception. And await is a way of saying, actually I want to wait for this, and in Perl 6 you can give await a list of promises, and it will give you back a list of the results, which is pretty convenient. If you excuse me, a slightly geeky one. Search for the first 100 palindromic primes. Okay, that's a prime number where if you flip the digits around, then it's the same number. They seem to come in bunches, it's kind of curious. So here we take the whole infinite range of positive numbers, which somehow magically fits in memory. Oh, okay, I shouldn't stand there. And then we grep out those number prime, and where the number is equal to the flip of itself. And then we take 100 of them. And I ran this on my desktop at home, and it ran for about 16 seconds. And I said, okay, that's a long time to wait. What if I use all the cores? So I stuck this in. I said, batch them up into groups of 512 numbers, throw them onto 6 different CPU cores, and then it ran in about 3 seconds, which was kind of nicer. I wrote a cache class, as you do, and then I want to use it from multiple threads. So what I'd like is that you know, when I add something or when I take something out, I mean, this is very simple logic here, but you can imagine it being a little more involved. And I say, well, I'd really like to have some locking around each of these methods. But of course, if I do that manually, and then I come and add another method in the future, I'm probably going to forget to add the locking. Thankfully, though, there's a way to solve that. We use a module called OOmonitors, and then we just change class for monitor, and we have automatic locking. Not bad. I want to write a script that actually runs other scripts for me. And whenever I edit the script that I'm working on, it stops any instance of it that's running, and it starts it again. So I want to watch files, or watch a file, and when the file changes, then stop it if it's running, and rerun it. So for this, we'll use a construct called React. And React is a way to write essentially something that processes events and does side effects as a result of them. I'm going to have a variable that says what is the current process that I'm running. And I'm going to say whenever. And I'm going to take the script, which is an IO path object in this case, and I'm going to say watch. And watch starts a file watcher. And it gives me a stream of events whenever the file changes. Now, if you've ever worked with file system events, you'll know it's horrible. Because, you know, you change the file once and it says, oh, have 3 events. And then you change it again and it says, oh, you can have just 2 this time. It's great fun. Anyway, we'll just use unique, so we only get 1 event per second for that file. It's kind of interesting that unique, you normally just use it to filter on the value. But in Perl 6, you can, with the supply, because it's asynchronous and because these are happening over time, you can do it based on time as well. And then the script change, so we kill any current process we have. That with is like an if defined, which sets the topic. And then we start a new process. We then say, well, if the process gets done, it terminates before we kill it. Just clear out that variable. That's it. That's how we can deal with processing asynchronous events. I think that's relatively easy. It also makes the hard things possible. So as well as all the nice high-level things that I encourage you to use, if you need them, you can get access to operating system level threads, locks. We even spread the CPU-backed atomic operations, which means we could implement things like lock-free data structures in pure Perl 6. Most of the time, don't use these. Unless you're the person implementing, the next exciting concurrent data structure, or new parallelism paradigm, or concurrency paradigm for Perl 6, in which case, there they are. A Polish language offers whip-up ability. The idea that we see a problem and we say, I need to solve that quickly, and then we go and find some nice, neat solution to it. That means that we're normally taking existing components and trying to stick them together. And we can only do that if there's some common interface between them, if they can talk to each other in some good way. In Perl 6, we, from the very start, have had a couple of types that are all about asynchronous data. We have promise, which is for a single asynchronous value that is produced by some operation, any operation. It could be code, it could be based on time, it could be based on some network operation. Doesn't matter. It's a common interface for something that produces a value at some time in the future. And then we have supply for things that produce a stream of asynchronous values over time. And just to give you a sense of how useful supply is, all of these things in Perl 6 are modeled as supply. So packets coming over the network. That's a stream of asynchronous things arriving. Those can be processed into a stream of WebSocket messages. Or if we're sending the WebSocket messages, vice versa. The file system notifications you just saw. Or outputs from a child process, user interface events, timer ticks, domain events, where we say, oh, this exciting thing happened in our application. All of them can be modeled with supply, and that means that we can write logic that deals with multiple of them at once as well. That's a great unification. A Polish language will torture the language implementer for the sake of the language user, and oh God, don't I know it. That's, I guess, a diagram of, sort of what my eyes look like after trying to solve some problems. It also says MN. This is the idea that we have M high-level tasks scheduled over N OS-level threads, where that's many of them, and really that's like about the number of CPU cores we have. So we could have, thousands of things going on concurrently, and just juggle them over a small number of threads, so the operating system doesn't have too much to juggle, the garbage collector doesn't have too much to synchronize, and everyone is happy. So we have await, which you saw before. And await really just means, well, suspend the current high-level task we're working on until the thing, or in some cases, many things that it needs become available. If you've, who's worked in another language that gives you await? JavaScript or ES6? Did you, sorry? Erlang, yeah. Did you spot something missing in my example earlier? Where's the async? Because we all love refactoring our code so that we can have all of the callers be async, right? No, we don't. In Perl 6 there's no async. You just await. And it says, okay, I'll just take the whole stack, save it somewhere, and when we get back to this task, we'll just schedule it somewhere and continue running it. That's decidedly harder to implement, but it's definitely a lot nicer to use. A Polish language also helps us to do the right thing. So earlier I showed you that React syntax, and we also have a syntax called supply. And that is for when you want to process events, but you want to produce a new stream of events as a result. And you say, well, what does that really give us? You know, it's syntax. So, yeah, it's pretty. You know, it's kind of nice that when you're writing code processing an iterable sequence, you can do a map, but you can also do a for loop. And maybe whenever is a little bit like, you know, the asynchronous equivalent of for loop. In fact, it does really work like a loop construct. But what's important here is not really the syntax, it's the semantics. Because let's just consider how this code can behave and how things can go wrong. So let's explain what it does first. It's called timeout. We take a source sequence of asynchronous events, and we take a timeout, which is some real number of seconds. We say supply, and that means we're going to produce a new stream of events. And at first, supply does nothing. It actually does nothing until something actually turns on the stream. And we say whenever this source that we're applying the timeout to produces an event, just emit it. And on the last time that it does that, when we reach the end of the asynchronous data source, and there's no more data, we're done. And done means, you know, we don't actually have to do anything more. We convey that this sequence has reached an end. That is the sequence we're producing here. And then we also set up the timeout. So we say whenever this promise in this number of seconds is kept, just throw this timeout exception. So basically, pass on the events. If we see the end of them, we're done. And if the timeout happens before, throw an exception. And that's an asynchronous exception that will be passed on to whatever is consuming the data here that we're processing. Now, there's so many things that if you were writing this without the supply whenever syntax, you'd have to think about. For example, when we subscribe to an asynchronous data source, we go and we register some kind of, you know, fundamentally some kind of callback, and that can acquire some kind of resource, and we need to release the resource. You've maybe debugged something before where you had event handlers and you set them up and you didn't release them, and then it leaked. Not very good fun. So if the data source completes, then we've reached the end of that, but we want to cancel this timeout. That just happens automatically for us. Vice versa. Maybe we're holding some resource producing this, this source of data. If we hit the timeout, then we want to close and unsubscribe from this. So we turn off the source of data. Again, it just happens. What happens if this underlying source of data here throws an exception? It will automatically be passed on, and we'll cancel this timer as well, because it's not needed anymore. It just happens. What if the thing that is interested in the data we're producing loses interest and unsubscribes from us? Well, we'll automatically unsubscribe from these data sources as well. Doesn't matter terribly much for this example, but there's also automatic concurrency control. This can be delivering events to us on one thread. The timer can fire on another thread. But we can trust that we'll only be in one whenever block in here at a time. We have automatic concurrency control there. That's a lot of things, a lot of bookkeeping taken care for us by a relatively small amount of syntax. The syntax design here is kind of nice, but the semantic design here is even nicer. Even if we remembered to do all of those, it would be a lot of boilerplate. Instead, we just do the right thing. So, I hope that has given you a feel for the essence of the PerlSix concurrency and parallelism model. What I want to do now is move on to talking about the application of PerlSix concurrency and share with you some of the things that I've been working on for one of my customers over the last year. The application is called Easy. What is Easy? So if you have insurance companies or reinsurance companies or undertakings, they have to calculate for the European regulator some standard formula. And when I say a formula, I mean this absolutely gigantic thing. I'll tell you how big it is soon, but it is an enormous calculation. And that's to demonstrate that they're solvent. And then they have to take this calculation and they have to report it to the European Supervision Agency or Authority, and that is done with something called XBRL, which is basically a massive load of XML that contains all of the data and the calculation results. That's kind of interesting-ish, I guess. Now, this calculation is very involved, and it changes over time, and that is not something that we really know about and have implemented. In fact, something that mathematicians at our client are working at. And so they can do that, we built something called EasyLang. EasyLang is a pure functional language that is not Turing complete. Yay. Which means that we can reason about it. And fundamentally, it means that the entire calculation forms a directed acyclic graph. That means that we can very easily answer questions like when the supervisory agency comes along and says, you have this number, where did the values come from? We can look at the graph and we can say, oh, they came from here, here, and here. This is the input data that produced them. Or, if we change this input data, what does it affect downstream? Oh, well, it affects this, this, and this in the graph. That's kind of neat, and the syntax for that is inspired by PerlSix. It's almost a subset, a very tiny subset for writing these formulas. And EasyLang was easy. We pass it with a PerlSix grammar, which produces a tree, which we walk to evaluate the expression. PerlSix is really, really good at this stuff. But that's actually not what I want to talk about today. Well, I kind of did, so I just talked about it. But okay. The architecture of Easy is actually, in terms of the high-level picture, pretty standard. There's a back-end application, and that's written in PerlSix. We use Crow to expose a HTTP API, plus serve some static files. And then we have quite a lot of components in there, and I'll just mention two of them, the main ones that I want to talk a bit about today. We have a versioned input storage. So whenever somebody changes a value in this, for audit purposes, we need to know the full history of that and who changed it and so forth. There's also a whole load of sign-off stuff where there's a 4 eyes principle, so different people have to sign off on the data. And then we have something called a live data set. And as the values get changed and the inputs get changed, we have to live recalculate the changes in the results. And we use the graph to know what we have to recalculate. Then there's the front end, which is written in JavaScript. I don't need to say very much about that. And these communicate over HTTP. And we have a WebSocket where whenever the calculation result changes, even if another user did that change, then the WebSocket will send out notifications to the front end, which will then reflect them. So we used Crow for the web socket and HTTP part of this. Crow has worked pretty nicely. These days it also has things for writing tests, so we could test all of our route handlers. That's pretty nice. This has worked pretty well. Crow itself is built upon the supply model. So we have a set of TCP packets coming in over the network, and then we feed them into a Crow HTTP request parser, which spits out a supply of HTTP requests to process. And Then we process them, and we have a supply of responses, and the responses go into a thing that serializes the responses and spits out a bunch of TCP packets. And that's basically all node-cro does. Well, okay, to hand-wave a lot. So we have all of these nice things. WebSocket support, reactive middleware. So when you write middleware, I mean, you're just processing a supply of requests or a supply of responses. That's kind of neat. And it also has integration with a module called log timeline, which is something that I built fairly recently. And log timeline lets us build tools that let us get insight into the processing pipeline. So I can see things like this. Okay, this is we have request processing. And I can look at this, and I can immediately see that we have up to 6 requests being processed in parallel there. The lanes of the same color are showing us things that happen in parallel. And you can notice that I can drill down into it. I can also see what each of these are. We can log some metadata. So Crow here logs which URL is this. I'm very curious about this request. Why is it taking so long? What in the pipeline causes it? And so we drill down, and we see something like this. And you can see for each request, we have these breakdown of the different steps, and we can say, oh, actually, it's this bit of request middleware that is eating all the time on that request, or eating most of the time, like 80% or more. So this is kind of nice, and you can see that we have the breakdown for each of the parallel requests as well. So there's quite a lot of information in there to help us understand the asynchronous flow of application. But I didn't just build this so we could visualize HTTP pipelines, though it's very nice for doing that. But so that we... oh yes, okay, you can see the cost of each stage. I did it so that you can visualize your own asynchronous, concurrent, and parallel applications in Perl 6 with it. And this was more useful than I could have imagined. It actually taught me things about the application I was working on that I hadn't really realized before. So let me talk a bit about the model, because the model is the thing the mathematicians are working on. They take the European regulations, they turn them into lots of formulas, and we load this at application startup, but when they're developing the model, we also have to live reload it on changes. And so the time it takes to load this model is kind of important. I mean, it's not like it's every single request we load the model, but if you're developing it and you had to wait around for a couple of minutes for it, this would not be pleasant. How big is the model, and what is in it? The model consists of 330 modules, which together are about 100,000 lines of YAML. Inside of that YAML, there's all kinds of configuration of the model, of the inputs that are required, of what types they are, of the kind of components they need, of the translation key for the text to put on the user interface for them, and also the formulas. There's about 4,000 formulas in this model, the current one, which correspond to 25,000 lines of EasyLang. So basically, I wrote the compiler for this language, and its first real program is 25,000 lines long, which is okay, fine. This is actually more code than Easy itself. Yeah. Now, of course, we're doing pretty interesting stuff here. So there has to be some Excel. There's 64 Excel documents. And these are based on legal requirements from the supervisory authority they provided. And we have to pull all sorts of data out of those Excel documents, including doing really, really fun things. Like we have these layouts where they have tables in them. And like there's grids of tables and tables of tables, and we have to extract them and figure out that this bit of data goes with this here and this here. And the rules are crazy, so it's great fun. And parsing Excel like that is not very fast. So what we actually do is get all of the data out, and just so you can see how big the Excel file is, it's like 7 megabytes worth of JSON just for the bits we need, which we pull out and we dump so we don't have to do all the Excel stuff every application startup. And what else do we have? Okay, yeah, of course, there should be some CSV in every good project as well. Not very much of that, only 5,500 lines, that's fine. And then we have some PO files with translation keys, and I think these are not entirely complete yet, so there should be a lot more than 2,000 translations. But okay, that's what we have. So that's the model. It's we're not quite big data here, but we're not exactly trivial either. And model loading, as the model grew, because it started small, and it grew, and it became long enough to be annoying. And we're really busy implementing lots of features, and they said, well, this is, it takes a bit too long. Is there anything you can quickly do about it, so we can develop the model faster? Because it was getting, up towards, 50 seconds or a minute. That's too long. And I said, okay, can we parallelize this? Is there some opportunity to use parallelism to do better? So whenever you do this, the first thing you have to do is look at the data dependencies. And just to tell you, this green thing at the top is the overall load time, and then we break it down, and we have to load some things called parameters. We have to load some layouts. This section here, with the blue and the purple, is loading modules and compiling modules. And then there's this little phase at the end called check. And the check phase is basically the link phase, where we take all of the different modules that we've loaded and we check all of the references between them and make sure that we don't have references to formulas that don't exist, and if we do, we complain. And actually, that is the only phase that really needs all of the information. The modules we load independently and compile independently. So those we could really do some parallelism on, some data parallelism, I guess, on those, and that's an opportunity. And actually, it's not until that check phase at the end where we need to check that they don't reference parameters and layouts that don't exist. So this looks pretty promising. So I said, okay, what we're doing is we're doing the same operation on many things. We are loading many of these modules and compiling them. This is a data parallel problem. So, okay, here's the code that loads the modules. So we take them, we grep out from the directory in all the YAML files. We then map them. Now this easy log thing here is actually from log timeline. And let's just get rid of it so we can see this code a little bit better. So here we have the loading. And can we make it parallel? Okay. Well, we want to just do the grepping out of those. That's really cheap. We don't need to distribute that. But remember hyper or race? Yeah? There we are. Just stick that in. Now when you do this, you have to be careful because we have this thing called problems. And the problems is a class which basically just collects together all of the problems. I think there's a little bit more to it than that, but that's simplified what it is. And we could potentially have some data race on that errors. So how do we solve this one? Make it the monitor. Make it the monitor. Solved. So I did this, and I reran my shiny visualizer, and it looks like this. Oh yes. Who wants this? Yeah, yeah. I'll tell you where. It's freely available. Okay. So it took 30% of the time it used to, and I was pretty happy with that. That seemed kind of nice, especially because it only cost like 1 or 2 lines of code to change, which, that makes me happy. Of course, it cost that because I designed the thing fairly well in the first place. but, you know, if you ask a compiler person to solve a compiler problem, then they probably should be doing a good job. You can actually see, by the way, the number of lanes tells you the parallelism degree in these diagrams. So it's kind of nice. So we're doing up to 6 in parallel. Big improvement. But I wasn't completely satisfied because I thought, well, maybe there's a bit more we can do as well. Because these two, and actually all of these, don't depend on each other. We, you know, the parameters and the layouts and the modules, we only actually need them for that check phase right over there. So we could do task parallelism here. We could just start all of these and let them all get on with it, and then pull them together to construct the model object and do the check. So I took this and I said, let's load this asynchronously. So we'll stick a start expression in there, and we'll then get back a promise, and later we can await it. What's wrong with this? Sorry? There are no comments. Come on, I named it all beautifully, man. No, that's not a very big problem for here. That's not the big problem. Exceptions? No, no. If there's an exception, then the promise will be broken and it'll get handled. No, I'm going to wait it later because I want to set more things off. Okay? Laziness. Oh, laziness. Okay, so what will happen is, yeah, I mean, map is lazy. So we'll quite quickly keep this promise, but we won't have really done the work. So, yeah. So this is just, you know, look out for this if you're doing this kind of thing, and all you need to do is stick an eager on there. Okay, laziness is great apart from, you know, when you actually want the stuff done. So, okay. And then we applied the same solution to the parameters and to the layouts. That was pretty easy. Notice that this problems thing gets passed, but we already fixed that, so we're all good. And then at the end, when we go and create the model object, we just await all the things, and there we go. We have the those loaded in parallel too. So I did this, and I excitedly plotted my my diagram again, and look at that. Yeah. Task parallelism and data parallelism all together. Very exciting. Could a little bit more time off it. I mean, you know, we're getting to the point where we're doing a lot of contention over resources at this point, so it's an improvement. But when I was looking at this, I thought I was done. And I was just looking at this diagram, and sometimes you just spot something. Does anyone spot anything interesting? Let's look at this part. Yeah, here we have a huge module that takes quite a lot of time, and it's being loaded at the end. And then we compile it. That doesn't take very long. So I've got all these nice shiny CPU cores, and you know, one of them is like, oh, do stuff, do stuff, do stuff, and the others are just like, oh, rest at last. I want them to work. So yeah, someone actually came up with the complete hack solution that I did for this. You just take that, and in here you, yeah, sort by file size descending. Yeah. Total hack. Completely worked. So by now we were down to 20% of the time, and I'd spent like not very long on this at all, and the customer was happy, and we could get back to features. And I actually haven't had to revisit this again since then. So that's nice. So the parallelism was very helpful for that, but as I say, parallelism, you know, it gives us it's in the solution domain. It gives us a better solution to something we already really solved, just we're faster now. But Perl-6 is good at concurrency too. And concurrency, as I said, is much more a design level thing. And we had to implement these live calculations. So we have data sets. And a data set is a set of inputs that we use in order to then calculate all the formulas. And there's about 250,000 inputs in the current test data set that we're working through. Probably a real one is a little bit bigger. But again, it's not that small. And we actually pull all of this into memory. So we can do these live data sets. Because, it's a big data set, but it's, again, we're not doing big data here. It's not small, but it's big enough. So what happens when you change an input? We do a HTTP post, which goes off to a crow root handler. And it shoves it into a database. Okay, and that's pretty boring so far. But it also makes an event. And it emits that event. And that goes into a propagation queue. Because doing the recalculation might take a bit of time. So at this point, everything is asynchronous. The HTTP request is completed. We send the response back off. And the event is sat in a propagation queue. And then we emit an object, which is a batch of changes, into the live dataset. And the live dataset looks at these changes and looks at the graph of the calculation and figures out which bits of the calculation or which modules in the calculation have to change. And the live dataset spits out another event. And that's also on a supply. And then the WebSocket handler is subscribed to that supply, and it spits out a WebSocket message. And that's the cycle of input processing. And we get a nice bit of batching here, which is quite helpful. So here's how it looks in the graph. So here, this little blue bit here is the HTTP request. So here we have the HTTP request, we run the handler, and then we're making the response. And the handler, as part of it, emits the event. And that's where the recalculation comes into effect. The propagator says, let's recalculate. And each of those things there is a module that we recalculate. The alternating shades of blue, different modules. So that runs in the background. The HTTP request completes nice and quickly. The user is happy. And later we get the updated calculation. Notice that actually the time scale along here, I mean, this is all well less than 1 second worth of time on this graph. It's sub-second there, but still, it's good that we can respond to this in very little time. So let me show you a little bit of the code from this, and the live data set is pretty involved. There's all kinds of things going on in there, but fundamentally, this is what's going on. We have the data set, we have a supply, which is the source of input events that we need to process, that is change notifications from the input store. And then we have a supply of changes, which is the events where the live data set said this value changed. And what we do in this object is we start a reactor. And the reactor takes this data source, that's a supply, and you can actually, just like you can take an iterable thing, like lines from a file or an array, and grep it, you can also grep live data that is being pushed. So the data flow here is that we emit an event and we push it through the grep, and if it matches, then we push it into this whatever. And then we look at it and we do the calculation. And somewhere deep in the calculation, we've calculated a module and we might have some formula changes. And if we do, then we emit an easy live dataset change object, which carries details of what just changed. Back over in the root handler, this is the crow code for setting up the WebSocket. So we get a request to this URI, that is /easy/setup WebSocket. Crow is kind of neat in that it uses Perl 6 signatures to do its dispatching. And what it actually does, because as always, if you give a compiler geek a problem, they write a compiler, is it goes and introspects all the signatures of your roots, and then it compiles it into a regex, which uses the NFA matching from the regex. So you actually get longest token matching semantics over your URLs, which means that you can actually reorder things and they behave as if you hadn't, because it picks the longest route that it can. So then we take the current user, we have the application here, and we say, well, with this user, get the current application state. And then we say, well, actually, we're going to make a WebSocket. We're going to upgrade this GET request to a WebSocket connection. And when we do that, we get an incoming supply, which is a supply of WebSocket events that are coming to us. We don't actually have any in here. And we return a supply, and Crow will subscribe to that, and anything that we emit on this supply, it will automatically send over the network as JSON to the browser. So all I have to do in here is obtain the live data set for the particular data set we're looking at, and say whenever there's a change, take it, turn it into JSON, and emit it. We're done. That was pretty easy to wire up. There's actually a little bit more going on in the real code, but again, this is the essence of what is happening. This is copy paste and delete a few extra conceptual things that don't matter here. We also did some extra bits. We data parallelized calculations of modules where they have many instances. So we have some of those 300 or whatever modules, a multi-instance. So you have many instances of the module. And when there's thousands of them, you can speed up the calculation by throwing it over multiple cores. It's just another .race somewhere. We also use channels. So there's a few times where you have the live data set, and it's recalculating things, but we also want to ask it to do some other calculation. We have a formula tester, where you can just run any formula. And you can imagine it would be pretty bad if it's in the middle of recalculating, and then you try to use some of the data, and you get a halfway state. It would be very confusing. So we actually send those to the live data set, and because it's written using a React block, then it only is in one whenever message handler at a time, so we know that if it is handling an evaluation request, then it will not currently be recalculating, by definition. So we get quite a lot out of that as well. I think Perl 6 has worked out very well for this. What I wasn't told before I started working on this is that the application we were replacing had performance problems. Notable ones. And our design is much faster. It's being written in Perl 6 is not a differentiator in that Perl 6 is a faster language than whatever it was before. It's getting there, but it's because we had a good design, and because Perl 6 is object-oriented nature, and all of the concurrency features that we had to hand helped to model the requirements and evolve that model as we better understood them in a really good way. And that is what gave us, I think, a design that is a performant design. And meanwhile, again, parallelism got us a bunch of easy wins on the side. Pun not intended. By the way, one thing I didn't tell you is the live data set is a live view. Sorry, the timeline is a live view. So you can watch what your application's doing in real time as well. Yeah. Yeah, there we are. Yeah, one more time. There we go. Okay, so we're almost there. We're almost at coffee break. Thank goodness does my throat need it. The future of Perl 6 concurrency. There's so many little things I'd like to do. We have a pretty good story on a lot of things so far. And, you know, I've really enjoyed using this. Not just enjoyed, not just enjoyed and, you know, it's fun, but enjoyed as in I felt like I could solve the problems I had in an effective way. And I could model the problems I had in a language that was cooperating with me in doing that. That felt really good. But there's something that, you know, I feel is still a big area we need to address. Something that might turn out to be kind of a differentiator, even beyond what we are so far. The other thing is safety. Because when I had that problems thing and I said, oh, we need to go and make it a monitor to be safe. That's kind of hinting at the sort of risks that we have. The situation is kind of like this. So there's smart folks who, you know, feel the future of programming languages is those that are very statically typed, that have very clever type systems, that do a lot of interesting proofs on the program. We also have some very smart folks who say, oh, when you build a system, build everything as late bind as possible so that you can evolve that system over time and understand it and introspect it and so on and see what is going on. I don't really, you know, need to preach to the choir here about the reasons that people might prefer dynamic languages. You know, we hear things like this. We need to write tests that assert correctness anyway, or it's easier to debug a concrete situation than some theoretical type error that I don't understand. Maybe there's truth in these, but they hinge on an assumption. And that assumption is that the test will reliably fail if the thing is broken, and that when we run the thing under the debugger, the bug will happen. What if the failure is a data race that actually has its effect one time in 10,000? Then we're not in such a good place. We kind of need reliable failure. I need a better word for this, but really fundamentally we need a Perlish solution to this. I don't believe we can get very far by saying, okay, Rust has a nice story here, let's do what they do. Because then Perl is good at stealing things, but you actually have to be good at stealing them and putting them together and making a coherent whole. This is kind of a research problem, but you know, I think it's one we should try and take on. Why? Well, because then we can make getting the easy things right easier. And we can make getting the hard things right possible. And maybe we can make the whipped up concurrent and parallel program that you just throw together more likely to be doing the right thing. And yeah, because we torment the language implementer for the sake of the language user. But I think these are the things that, you know, define a Perlish language. And one of the things I really, you know, enjoy about using Perl is these kind of define a Perlish library too. People write the synopsis of what it does, so you can look and you can see how to do the easy things. And I think, you know, being easy to get into and whipping up ideas together, trying to do the right thing, and trying to realize that others are trying to do the right thing. I think that to me seems like a way to be a Perl community too. So thank you very much. I hope this has been of some interest. I have no idea if I have time for questions. Oh, I have 1 minute for questions. That is precision. So, or maybe I have 5 minutes for questions. What time am I meant to end? Is it 5 past or 10 past? 10 past. Then I have lots of time for questions. Somebody ask a question.
What's the difference between a hyper and a race that you used in different slides?
The difference between hyper and race is that race does not preserve the order of the results relative to the order of the inputs, and hyper does. This isn't about sorting. It's just saying, you know, if I have the list of prime numbers and I feed them into a grep, then with a non-parallel one, of course, they come out in the same order as the inputs. And if I did a hyper, then that will be true of the parallel results, so it will batch them up and then it will put the batches back together in order. And with race, it won't do that. And the decision about which to use is simply, do you care? And if you don't care, then you can eke out a little bit more performance.
So the problems object that suddenly needed to be turned from a class to a monitor, that's because you put in a race sort of upstream of that, right? What do you think about the prospects of statically determining that that needs to be done, like getting a nice tip or warning of that?
That's a really interesting question, because Perl 6 is... Oh, I thought it was to the microphone, but okay. So the question was basically, can we statically analyze the potential for needing a monitor instead of a class? Or in general, I guess, can we statically analyze those sorts of problems? So that's a really interesting point. And that ties into this research that I was talking about at the end. And Perl 6 is really interesting, because we maybe say Perl 6 is a dynamic language, but Perl 6 is really two languages at once. It's a staticky language in the lexical sense, and then the objecty sense, it's a very dynamic language, because part of the definition of object orientation is late binding. So for the staticky bit, can we come up with something where, as well as being, like the Perl 6 types, we can analyze them at compile time, and then we can enforce them at runtime at latest? Can we do that for what we come up with for detecting concurrency problems too? I hope so, yes. Either that it's an analysis that is fast enough that we can put it into the compiler itself, failing that it is an analysis that we can do and grind through in the background in a, an IDE or linter or something like this. Any more?
So I didn't get the easy, or was it called easy language?
Easy lang.
Can you just more tell some details what this looks like or what it was?
Easy lang, I mean, it looks like Perl 6, but only a very small bit of it. Basically, it has literals. It has standard mathematical operators. You can call functions. There's a load of built-ins. There are very restricted lambdas, and we restrict them so that you can't ever actually store them, and that means that you can't ever do recursion, which means you can't be Turing complete. So yeah, there's actually the only looping we have is mapping over data structures and things like that. So again, we're not Turing complete there. But yeah, I mean, it's basically a very restricted small subset of Perl 6. It looks a bit like a Perl 6. The only real departure is because everything is functional, then you can put if anywhere. So you can write if blah 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 plus if whatever, and in full Perl 6 you'd have to put do. And just because everything is functional and evaluating to an expression, then that felt like a sensible thing to do. But yeah, basically it's a slightly twisted, very small Perl 6 with very carefully designed language features, so that the whole calculation is just a directed acyclic graph.
To make the class be a monitor, you used a new keyword. In Java you can use synchronized. Why not use an extra keyword and be it applicable to other things as class as well?
Okay, so the question is why do we have the monitor keyword, and why don't we maybe have some other keyword that we can attach to more things? I mean, fundamentally, it's basically just doing what fits with the Perl 6 language design overall. In Perl 6, we try to associate new semantics with new words, new meanings. That is why we encourage, for example, when you have an operator and you thinking about overloading it, but you might put a different meaning on, so you take plus and you think, okay, let's make plus mean something that isn't really numeric addition. In Perl 6, we say, no, don't do that. Define a new operator. And it's kind of the same when we have packages, and packages come with their own behaviors. So grammar is like a class that inherits from a different base class. Why don't we have grammar as a modifier on class, or we make you write is grammar? Well, just because we feel it's worth calling out the distinction at the point we say what it is. So it's just a consistency thing, and it's just using the extensibility we have in the places we have it. To me, that feels like a natural solution for Perl 6. Also, this is done as a module. It's not something that we've done directly in the compiler itself. And some people sometimes say, shouldn't it be in the compiler? And the answer is sort of, maybe, kind of, but not quite with the semantics it has at the moment. Things should be really well thought out before they go into the language as a whole.
I have my own question, maybe a small question. So for that data parallelism stuff early on, where you added about 3 lines, did it take less time to do that than to write the slide describing what you did?
Did it take less time to write the code than to write the slide describing the code? Yes, because I screwed up the animation the first time I did it in PowerPoint. Yeah, it didn't take long. In fact, I spent more time staring at the visualization, like being, oh, this is so pretty, than I did writing the code. So, yeah.
Any more questions? Well,
No? Okay, and I'll just comment, if you're curious about the tool that does the visualization, the protocol is an open one, and we've documented it in the log timeline, so people can build whatever tools they want. But the visualizer I showed is the one built into the comma integrated development environment. And, sorry? Promotional? The free version. I put this in the free version, okay? So, because partly because I wanted to be able to talk about it here, but more importantly because I actually think this is a really important thing to have. And once I built it and saw it, I'm like, this can be a difference for people using Perl 6. It can be a reason for them to use it, and it can be something that really changes the game for people who are using it. And I really wanted to share that. Comma has been successful for us in that it's actually helped us promote our competence in building such tools, and that has worked out very well for us. So. As a company. So to give this feature freely, I gladly do it, and I hope you'll enjoy it. So.
Well, I guess we applaud and then go to coffee.
Coffee, okay. Thank you very much.